Welcome to Module 6 of the No-Code Blueprint, How to Design Data Structures. Now, this is, I would say, the most important module of this course. Yes, the business logic one is quite important, but when it comes to data structures, this is where I find that most people get unstuck when designing and implementing their no-code solutions. So there really is a lot of important topics in this module, but let's get started. So what are we going to cover? Well, firstly, we're going to talk a little bit about different types of databases, and there is quite a lot of detail that you can go to, but it's fairly technical and probably not necessary for what we want to achieve. However, that detail is available in the notes that come with this course. So if you are interested and want to delve into some more detail, those notes are there for you to refer to. But we're going to touch on the key differences briefly. And then we're going to go into some of the concepts of databases. And there you can see those there listed out as items 2 to 7. And then we're going to end this module with a practical exercise, which I am looking forward to. So let's get started. So in an earlier module, we spoke about different types of databases. We mentioned relational databases and other types. Generally nowadays in the, not necessarily the no-code world, but in terms of the internet type applications, there are two that seem to be prevalent, and those are relational databases, things like MySQL or Microsoft SQL Server, and then NoSQL or document databases like MongoDB and those sorts of things. Now, there's various differences between them, and as I said, I didn't want to make this overly technical, but just wanted to make you aware of these differences, and feel free to drop to the written notes if you do want to explore the topic further. I think the key differences between these two are the way that they handle data models. Where relational databases are more structured, whereas document or NoSQL databases are unstructured, and this means their schemas then are different, because the relational databases have the structured schema, whereas the other ones do not. There's different ways in which they address scalability. So, for example, as your application grows, again, this is not necessarily something you need to worry about, because the no-code platform will handle those sorts of things for you. It's only when you move beyond those platforms you need to start thinking about these things. The way that data is queried and extracted in these two database types is different. And the way that these databases enforce consistency is different. So typically relational databases are really important, where applications need to have accurate data and complete data. Data can be a little more flexible in the NoSQL or document databases. And finally, this really boils down to the sorts of use cases that you want each one to solve. So I think, generally you'll see relational databases are used in things like financial systems and healthcare systems and those sorts of things. And the NoSQL or document databases tend to be used for a lot of social media platforms like Facebook or Twitter. I think the important thing to note, though, is on most no-code platforms you'll be using, like Bubble or Glide, these will connect to either their internal databases, but do allow you to connect to external data sources like Excel or Google Sheets or Airtable. And some no-code tools also allow you to actually go beyond that and connect to external databases like MySQL or MongoDB or those sorts of things. I think then, in just closing on the slide, a database will have to reflect the real world that your no-code is serving, your no-code application is serving. But before we get into some of that and think about how that works, let's look at some of the basic tenets of databases. Overall, we refer to this as the entity attribute relationship model, meaning that we will predominantly focus on relational databases. So first, we have the concept of a database itself. And a database is essentially a collection of data items, generally tables, but also other things, as we'll see when we go through the examples. Generally, you would have a single database for your application. Next, we have tables, and tables can be seen as a sheet really, made up of columns and rows. And a table will generally represent a real-world entity, for example, a customer or a product or an order. And each table is made up of columns. So you'd have in a customer table, we might have a name column, an age column, an address column, a gender column, and a VIP status column, for example. And then, of course, rows. And in this example, each row would then represent a single customer. So firstly, let's look a little bit more at columns. As I previously mentioned, columns represent attributes of the table. So each column will have a data type based on what you want to store in that column. So going back to our previous example, if, for instance, the first column was customer name, we would have a data type of text. So that means we can have numbers and special characters and letters in there. Date of birth would have a type of date, so we can only put dates in that column. And VIP customer status might have a type of Boolean, which is a true or false indicator. We could also store that as a 0 or a 1 or a Y or an N. So again, all of those are sort of up to you when you design your data structures. Each table should have a column that's designated as a primary key. And this is important because it identifies or uniquely identifies a row or a customer in this case as unique. And in this example, it might be a customer number, a customer account number, and we'll talk about why it's an account number and not the customer name in a subsequent slide. The primary key also helps identify the database to find, or helps the database find records faster. And other columns may also have indexes on them, and this is to speed up the database again, but also to help us join tables together, and we're going to cover this more a little bit later. Next, as we mentioned, rows will each row will represent a specific item within that table, so a single customer or a single product or a single transaction. It's really important not to confuse rows and columns. I know it seems obvious, but when you design your database, you may ask yourself, when I add a custom, should I be adding a column or a row? Now, going back to the pandemic, we saw this earlier on where there weren't any real applications to handle what was happening. So people were tracking things in a spreadsheet. This happened in the government. And whoever had designed that spreadsheet kind of made the mistake of each time there was a person that was found as COVID positive, they would add a column to that table. And eventually they hit the limit of that Excel sheet, which I think is 65,000 columns. And beyond that, they couldn't track any more infections and they lost a whole lot of data. Now, the right thing to do would be to add each patient as a row rather than a column. So fairly basic, but as you can see, these mistakes do happen in the real world. So do pay attention in terms of how you model what goes in rows and what goes in columns. Next, we have indexes. An index works like an index in a book, and this helps us and the database find individual records more quickly. So for example, if I were looking for a chapter in my book about Spanish cooking or recipes in my global recipe book, I wouldn't have to page through all of the pages to find them. I'd go to the index, see where the Spanish recipes were. It would tell me they're on page 147, and I can go directly to page 147 without wasting any time. Indexes in tables work the same way. Then we have keys. These work in a similar way to indexes, and they help us join data between tables. So for example, go and find me all of the orders in the orders table for a particular customer. This is very similar to the VLOOKUP function in Excel, which I'm sure you've used many times before. And then the way that we join tables together, or the way we relate them together, those are called relationships. So relationships define the links between tables and generally reflect the relationship between entities or tables in the real world. For example, a person can only have one current location. It's physically not possible to be in multiple places at the same time. So in the data world, you'd represent this as a one-to-one relationship. So one person, one current location. An order, for example, so I think from Amazon, can contain multiple products. So in this example, you would have a one-to-many relationship. So one order can have many products. Again, another example of a one-to-one relationship is that you can only ship an order to one place. But you may, in fact, when you look more broadly, have multiple customers. Each customer can ship to multiple locations, but a location or a house might have multiple customers. So ultimately, this becomes a many-to-many relationship, which does get a little complex to model. You probably won't have the need to do that for a basic application, but something to think about as you grow the complexity of your application. Again, another example of this is on Twitter. You can follow many people, and many other people can follow the same people, and this is also a many-to-many relationship. Again, many-to-many relationships are handled better in NoSQL databases than relational ones, hence the example a bit earlier of social media networks tending to use unstructured databases. Next, we have the concept of views, and views, as the name implies, provide a view of a physical table. We can use views to join data, to filter data, and to sort data, and present it to users. Now, this doesn't mean it necessarily duplicates that data. It doesn't. It only provides you a view over those data. So again, like using filters in Excel, the same sort of thing. Not all no-code products have this concept, but products like Airtable do have something very similar. And views are really are virtually in a way, as I've said. So if you change the data in a view, it'll change the underlying data in the associated table, but it doesn't duplicate it per se. Next, we have stored procedures. You may come across these if you are using a relational database, but in the no-code world, they might be called modules, or they might be called procedures, or they might be called components. And all of what these essentially do is they store a bit of code related to the database that helps you perform some sort of action. Right, now having covered some of those basics, we're going to move on and talk about the concept of a conceptual data model. Because data models can exist in various stages. The conceptual data model is generally where we start. And this is a high level of abstraction of the real world. And it describes your application's data model in very similar terms to the examples used at the start of this module. Things like customers, things like products, things like orders. And it's generally visually represented and shows the key entities or tables and the relationships between them. And at the end of this module, we'll go into an example and a case study where we go and do that. However, post this point, we will need to do some additional work to get this into a better shape to implement in our no-code platform. But before that, before we think about that or know how to do that, we're going to cover a concept called normalisation. So normalisation is the process of structuring relational databases to ensure that the dependencies or the relationships between tables are properly enforced. This makes it easier to update data where necessary, as well as extend your data model in future without too much complication. There's various forms of normalization. Generally, third normal form is the most common one that we use. Don't get hung up too much about this theory, but we'll look at the practical example at the end, and it'll all make sense. So, just to mirror this in the real world, for instance, you wouldn't want to each time, for instance, a customer orders something, you wouldn't want to recreate that customer record. You would only ever have one customer table and another table that contains your orders, and we'll see how that comes to life, as I said in the example. Please note, you don't have to be perfect at modeling this, but sticking to some of the core principles will give you the flexibility and ability to evolve your software and your data model to meet changing and new requirements, as well as making sure that the performance of your database is good, because designing the database in an incorrect way can really hamper or kill the performance of your application. Next then, once you've completed your data model, your conceptual data model, and you understand the key concepts of normalization, you take that to the next level, and this means creating a logical data model. And this is very likely the level to which you'll evolve your data model, at least on paper or in some kind of software, before implementing it in a no-code tool. And we'll be using the work that we create in the conceptual data model to then create the logical data model, so you can see how this evolves. And once you build more experience, you can usually start sometimes at the logical data model. Now, it also is worth mentioning that there is a physical data model, and it's not necessarily relevant to no-code solutions because the no-code solution platform will handle that for you. I've only included it here for your interest, but historically the person or persons designing a database would not be the same as those implementing it, and it was therefore imperative that the design specified the necessary level of detail to support the implementation of the database. And the physical data model would do this by stating the exact column names, data types, storage space required, and partitioning. So for example, where you had a really high volume of transactions, think millions, tens, hundreds of millions of transactions per year, it wouldn't be physically possible to store those in a single table, and it would need to be partitioned. But again, don't worry about that. That will be handled for you in your no-code platform. We've learned about keys and indexes, so these are quite important. Again, I just wanted to reiterate on them here, and I will draw out the relevance and importance of these when we do our exercise at the end of the module. Now, there are some other considerations, things that you need to think about, but many of the traditional considerations that a database designer had to manage are not relevant on no-code platforms. This is what makes it easier for us. In fact, many of these have even become less important on the cloud. Speed and storage are a good example. Previously computer hardware, things like processing units, RAM or memory and disk drives would need to be provisioned based on the software design. So software designers needed to consider this because changing the hardware was a costly and time-consuming exercise. Now on the cloud, it can be literally done with a few clicks. We shouldn't lose sight of this because both storage and processing power are important, and you'll see some no-code platforms do give you the options to scale. Perhaps when your application or solution goes into production and you start getting customers, you may need to think about that as your user base grows. But you'll see these reflected in the no-code pricing plans and tiers, and the different platforms have different ways of dealing with this. So for example, if you look at the free and lower tier plans on Airtable, you'll be limited to, I think it is 1,000 records or 5,000 records respectively per solution or database, which doesn't really go very far in supporting an enterprise or a multi-user application. You need to go to the bigger tier and pay more money to be able to have that amount of records. Platforms like Bubble have various tiers of processing capacity, and as your requirements grow, so will the price of your plan. So the final part of your design work you'll need to consider is, how many users and how much data you'd initially need to support. And then as your solution grows, what those numbers might look like. This is all important because if you're going to sell or charge for your product, you need to make sure that your costs don't cripple you and that those costs are recovered in what you charge for a subscription, for example, to your solution. It's also very important to note that while most free and lower tier price plans will support your immediate requirements, you need to think, can your chosen platform support the growth that you envisage? So, for example, the top pricing tier of Airtable at the time of this course only supports 250,000 records per database. If your requirement exceeds this, you need to consider an alternative. So, a stupid example, but there's no way that Amazon could run their business on Airtable because they probably process 250,000 orders in an hour. But be realistic, be realistic and think, though, is my product going to become the next Amazon in the short term? Don't want to shatter dreams, but probably not. So don't over-engineer things. Don't incur cost where you don't need to, but do think about the longer term. Right, so next we're going to do an exercise, and this is producing a conceptual data model. You'll see as part of this module, there is a text document included that talks about the use case in more detail. But essentially, It is an online store, so think about Amazon and the way that Amazon has structured and runs their business. And in this example, I'm going to be taking you through designing a conceptual model and then evolving it beyond the point of a conceptual model, thinking specifically about how we deal with products on that online store, how we deal with product categories, how we deal with customers, and how we deal with orders. So feel free to follow along in the next part of this module.